Okay, sorry about the delays. Welcome back to the course. So today is our third day. So there were a couple of changes in the schedule. I guess we are a bit behind the schedule, but I have just decided to just, I guess, like go slow instead of just going too fast. I guess I will adjust the schedule and the pace, and I'll try to deliver like ideas in more details, and so that you guys can follow and understand the materials. Okay. I'm also thinking about talking about some of my recent research on the last day, which could be a bit different from the materials that we are covering for the last few days. But I'm still debating between the materials. Okay, but I'll let you know tomorrow or before the last day. Okay, is there any question? Okay, forward for a second. Okay, so today, so lecture 5 is about one algorithm that's useful for computing a maximum weight bipartite matching. And the second topic of today of lecture 5 is about some application, which is related to economics. So there are two sides of players, and you want to, like buyers and sellers, and you want to determine proper prices for items so that we can match items and buyers without any conflict. That's the second topic of today. So let's begin. So yesterday we talked about on linear programming based algorithm for computing a maximum weight bipartite matching. Right? So the idea was that we saw one P relaxation, and if it gives us maximum matching, then we are good. If not, we kind of perturb the components of the solution, and we recover a matching with the same objective value. And that's how we obtain a maximum weight bipartite matching. But we're gonna talk about a bit more combinatorial. So it's not like we are getting a solution directly from an LP, but we still look at the linear programming formulations, but the algorithm is a bit more combinatorial. Okay, that's a Hungarian algorithm. So the Hungarian algorithm, its main component has to assume some structures on the graph. So we have a general bipartite graph that doesn't always have a perfect matching. It could also have some different numbers of vertices on the left and right. So we need to do some trick to transform the given graph to an input for this Hungarian method. So that's the pre-processing step. So the first one is the following. So we are interested in computing a maximum weight matching. So that is, if you have a negative weight, then you don't want to include an edge with a negative weight because you want to increase the weight sum, right? So in that case, we just discard, throw away edges which have negative weights. Okay, that is the first step. And the second step is the following. So discarding all edges with negative weights, we may assume that all edge weights are non-negative, but maybe the graph is not complete, right? In that case, we are adding some dummy edges with weight 0, okay? And then we just, we have a complete bipartite graph, and also maybe maybe left and right, maybe the left side has a smaller number of vertices than the right. In that case, we are just adding dummy vertices on the left so that we can balance the number of vertices on the left and the right. Okay, so then we get a complete bipartite graph where two sides have the same number of vertices. That is the pre-processing step. So we just deal with this complete bipartite graph and apply the Hungarian algorithm. And we can just ignore the whatever dummy vertices and dummy edges we added before. That is the idea. So let me explain the pre-processing step with this figure. So we have a bipartite graph where one side has 3 vertices and the other side has 2 vertices. And also we have this negative edge of weight -5. Then we first take out this edge with weight -5. And then we are adding 1 vertex at the bottom. And also we add all possible edges between 2 vertices from one side and the other side. Okay. So this is the pre-processing step. Now, after doing this, we can assume that our graph is a complete bipartite graph where 2 sides have the same number of vertices and the edge weights are non-negative. Okay. This is the typical input for the Hungarian algorithm. Okay. We're gonna now we can explain the Hungarian method. So basically we want to so we were interested in computing a maximum weight matching, but now we have a complete bipartite graph, and it must have perfect matching because we have added all possible edges between 2 vertices. So there must exist a perfect matching. And because we assume that all edge weights are non-negative, there exists a maximum weight matching that is a perfect matching. Okay. So now the question is, can we find the maximum weight perfect matching in this complete graph? So that is the idea. So again, we have this condition. Now, if you write down the linear program for computing a maximum weight matching, we have this thing. It's just that I have divided the vertex set into 2 sides, V1 and V2, left and right. And again, we know that there's an optimal solution that is a perfect matching. So you can in fact set the inequality constraints to equality, and that gives us the this linear programming formulation. Okay. I'm gonna refer to this formulation as primal because I'm gonna look at its dual in the next slide. If you get the linear programming dual of this formulation, we get this thing. Look at I don't have any non-negativity constraints on these y variables because I had the equalities only. Okay, so this is the primal, and if you take the dual, I obtain this formulation. Okay. Now we know that the strong duality holds for this pair of primal dual because again the primal problem, it has a finite optimal solution, so the strong duality holds, and at the same time something called the complementary slackness condition holds. But for those of you who have not taken linear programming, I'll give a proof for the following result. So let's look at the statement. Okay, this can be a bit technical for the first time. So let's go through the statement together. So let's say there's a perfect matching. Okay, and if you go back to this primal formulation, so if you take just matching that is not perfect, then that's not a feasible solution to this linear program, right? Because if you have this degree constraints that are given by equalities, you need to assign, so you need to match every vertex. Otherwise, if there's a vertex that is exposed, then that does not satisfy one of these equality constraints. Okay, so to have a solution satisfying all these constraints, you need to have a perfect matching. Okay, I have perfect matching. And also, I take a feasible solution, YG, to the duo. That means that, so you have a assignment on Y and Z that satisfy all these constraints. Okay. This is almost like the vertex cover formulation, except that the right-hand side has general weight. So yesterday, we talked about the minimum vertex cover problem, where the right-hand side was 1. But in general, we have these W's. Okay. So what is the statement? So let's say I have a perfect matching, a solution, feasible solution to the primer, and I have a feasible solution to the dual. And if these things, M and YZ, satisfy the following condition, then we can guarantee that my perfect matching is optimal. Okay, what is the condition? So for every edge that's used in my perfect matching, I want to satisfy this inequality constraint from the dual with equality. Okay, then by the complementary slackness condition, we can guarantee that my perfect matching is optimal. I'm gonna explain, I'm gonna prove this statement without resorting to complementary slackness, but that is a statement. And then before I get to the proof, what is, let me just mention the complementary slackness condition for those of you who are aware of linear programming. So complementary slackness is, so basically I have equality constraint right here. So I'm okay with that. But you take this inequality constraint from the primer, and these variables xe correspond to this inequality constraint. So we say that the complementary slackness condition is satisfied if x uv times yu plus zv minus wuv equals 0 for all uv. So this is the complementary slackness condition. And this thing holds if and only if xuv is positive. So what it means is I take this huv in my matching. Okay, so you have this huv in your perfect matching, then you have to satisfy the constraint for the dual with equality. Okay, otherwise the product will not be 0. And also, if there's an edge with that satisfy the constraint from the dual with this positive inequality, then you cannot use the edge in your matching. Okay, so this is the complementary slackness condition. Okay, so to satisfy this complementary slackness condition, I can only use an edge that satisfies this inequality, this constraint with equality. That is the main idea behind the Hungarian algorithm. Is there any question? Right, so I'm interested in, so the question is about the situation when all weights are negative. So if all weights are negative, then a maximum weight matching will be the empty set, right? Because then you just throw away all edges, and then all the edges after the processing step will be dummy edges. Then whichever matching you compute, we're gonna end up discarding all edges later. So that's just the empty set. Get it? Works. The algorithm works for that case too. Okay. Any other question? Okay, so let's prove this. First of all, I'm gonna prove the following. So somehow my Zoom has stopped. Sorry about the delays. Okay, so right, so let M be a perfect matching, and let YZ be feasible to the dual problem. And I want to look at the weight sum for this matching. Okay. And in fact, let me use notation UV. So this is the weight sum of the edges in the matching. And because YZ is a feasible solution, I know that individual WUV is less than or equal to YU plus ZV. Okay, because YV is a feasible solution. And the summation is taken over the edges in the matching. And I know that my matching is perfect. So every vertex is covered by an edge in this matching. So this is equal. So I'm gonna separate out the Y part and Z part, and each vertex appears exactly once. So this is equal to summation U in V1 YU plus summation V in V2 ZV. Okay, and this is the value of YZ, objective value of YZ for the dual. And this is my weight of my perfect matching M. Okay. What this shows is that the optimal, the weight of this perfect matching is always less than or equal to the value of this dual solution. Okay. And this is a short proof for weak duality, right? Well, let me not. Okay, this is a consequence of weak duality, but we gave this direct proof. Now, let me use this condition that I have this condition that my matching consists of edges that satisfy this constraint from the dual with equality. Okay. That is my condition. In fact, this thing has to be satisfied with equality. That is my condition. Let me write it down again. If yu plus zv equals wuv for all uv in the matching. This is the condition that we want to impose. Then summation of uv in m wuv is equal to summation of uv yu plus zv over all edges. So we have u in v1, yu plus summation v in v2, z. So this is strong duality. So what is the meaning of this? Well, we know that for any matching, perfect matching, and for any feasible solution to the dual, there's an inequality, right? The weight of this matching always upper bounded by the value of the dual. But somehow, if I impose a condition, then you can achieve the equality between these two. It means that, here, this weight of this matching is maximum possible, and the value of the dual solution is minimum possible. So that's the just to illustrate, give you so this is, let's say this is the distribution of yz values, and I have this distribution of the matching. And I know that there's always a gap between, the dual values are above any values for the matching, but then I somehow reach the equality. And that's possible only when, these two values are equal. So that's what I'm trying to explain. Okay, so this is the main idea. So using this property, so the idea is that somehow I run my algorithm, and at some point I have, if I construct the perfect matching that satisfies this equality condition for all edges in that matching, then I'm done. That's a proof for optimality. I end up computing a maximum weight perfect matching in this graph. Okay. So then the question is, how do we do that? Okay. And in fact, perhaps constructing a perfect matching is harder than satisfying that equality. So instead, what I'm going to do is I'm going to use edges that satisfy that equality. And I'm adding one edge by one, and at some point I'm gonna create a perfect match. Okay. So what it means is, the idea is, we satisfy the complementary slackness condition always. What it means is x uv times yu plus zv minus wuv equals 0. So this is possible. This is possible by using only the edges. With yu plus zv minus wuv equals 0. Okay. If there's an edge uv where uv plus zv is strictly greater than wuv, I'm not going to use it. Okay. I'm only going to use edges with the equality. Okay. But it doesn't always guarantee that you find the perfect matching. Well, that's good. I'm going to kind of adjust the values. And later on, I want to create a perfect match. Okay. Then we try to construct a perfect matching. Okay. As soon as you create or you get a perfect matching, due to the way I pick my edges, we satisfy the conditions of the lemma, then that proves that your perfect matching is optimal. That is the algorithm. Okay. So that's what I'm trying to get at. And so how do we implement that? Implement the idea of picking edges that satisfy the constraint with equality. So just to illustrate the idea, we're going to use this notion of equality subgraphs. So I just ignore edges where the constraint is satisfied with strict inequality. I only keep the edges with equality. That's the equality subgraph. Okay. Any question? Let me give you one simple example. So I have this graph u, v, and x, y. And I have a complete bipartite graph between this. And the edge weights are given by 2, 7, and 3, 5. Okay. So we know what is, we know a perfect matching, maximum way perfect matching. That is, we just pick ux and vy. Okay. Now I'm going to explain the algorithm, the Hungarian algorithm that computes up the desired perfect matching for us. Okay. So we need to construct a feasible solution to the dual. Okay. So we need to have yu plus zv at least the w, just to avoid confusion. For any edge uw, I want to have this yu zv assignments satisfying the inequalities. The most natural way is that for this value, I'm going to set zw to 0. Okay. And I'm going to assign yu to be max of w u w. Okay, w is a vertex and w subscript is a vertex, but no more w is the weight for all edges. So I look at this vertex u and look at all these edges that are attached to this vertex, and I take the maximum value of it. Okay. V. Among the neighbors of u, I take the maximum weight. So in that case, yu will have value 3. Okay, so you have ux has weight 2 and uy has weight 3. So I'm going to assign 3 to yu. And yv will be 7. Okay, and zx will be 0 and zy will be 0. Okay, then this gives you a feasible solution to the dual. Okay. And let me draw a table. U and v and x and y, and here each value will be for example, this one is yv plus zx minus wvx. We're going to record this value for each entry of this table. So here, let's look at the first box. So yu plus zx minus wux will be 3, oh no, 3 plus 0 minus 2. Okay, yu equals 3, gx 0, and wux will be 2. It has value 1. Okay. What about v and x? So yv equals 7, and gx equals 0, and wvx is 5. So the value is 2. What about this box? yu is 3, and wuy is 3, and gy is 0. So this is 0. And also you can say, see that, for hvy has value 0. Okay. So then again, the idea behind the Hungarian algorithm is that we can use the edges with 0 values. Okay, that's the edges satisfying the constraint with equality. Okay. Now what you do is you draw the equality subgraph. You v x y. You can use uy. Oh no. And you can use vy. Okay. So you need to. So only these 2 edges are available to you. So this is the equality subgraph. Okay. So for this one, you just run the augmenting path algorithm. Run the augmenting path algorithm on the equality subgraph. If you run the augmenting path algorithm, it computes a maximum matching. It doesn't care about weights, but it maximizes the number of edges in your matching and minimum vertex cover. So let's say I have a maximum matching, and minimum vertex cover will be just this vertex y. I cover and I need to adjust the variables and weights so that I can add more edges to my equality subgraph. So now I have the graph matching is not perfect. So I want to use more. I want to use more edges from the original graph. And in particular, there are edges that are not covered by this vertex cover. I want to add them to my equality subgraph. Okay. And this is a subtle point. But let me just state how the algorithm works. So what you do is, for this vertex, okay, so, right, now, great. So I take this value 1, which is the minimum value. But the way it is picked, okay, so among the edges that are not covered by this vertex cover, I'm gonna pick the smallest value in the table, 1. So I'm gonna increase the value of y to be +1. Okay. And I'm gonna decrease the value of u by 1. I'm gonna decrease the value of v by 1. Okay. I'm gonna explain how it works, but let's do this. Okay, just believe me that it should work. Then if you do this assignment, gy becomes +1, and yu becomes 2. Okay, and yv becomes 6. Let's compute the table one more time. Again, let's update the table. Okay, and in fact, you know, these two edges that were used in my equality subgraph always survive. You don't touch them. But if you look at ux, hux, y equals 2, gx equals 0, but wux is 2. So somehow we are decreasing this value, and now it becomes 0 right here. You can use ux together. But if you look at vx, it has value 1. It decreases, but it's not equal to 0 yet. Now, let's update the quality subgraph. We had ux, uy, and vy, and we are now having this at ux. Okay, we have one more edge. Now, if you run the augmenting path algorithm, it computes a maximum matching. And the only maximum matching in this example is ux and vy. And this gives you a perfect matching. Okay. And again, the way we design this algorithm, if you use, so any edge in your matching satisfies the constraint from the dual with equality. Now we get a perfect matching. So, and then by the lemma about the complementary slackness condition, we get a maximum weight matching. And then, in fact, in this example, we know that 2, 7 gives you a maximum weight matching, perfect matching. Any question? So I guess the tricky part or something that looks like black box is the way we adjust the vertex weights. Okay, but they are sophisticatedly done so that we are expanding the equality subgraph. We are adding more edges to the equality subgraph, and we are improving the vertex weights so that we are getting closer to the perfect match. And that is explained in the next algorithm, in the algorithm pseudocode. So we have a complete bipartite graph. And again, we have this, imagine this graph with y variables and z variables at the bottom. Okay. And for the bottom vertices, I said their weights to 0. Their variables to 0. And for y values, I take the maximum weight of these neighboring edges. And that gives you the first, straightforward, feasible solution. And then, we start by an empty matching and empty vertex cover. And so until we compute a perfect matching, we do the following. So we look at the equality subgraph just to use edges with satisfying the constraint with equality. And we run the augmenting path algorithm to compute a perfect maximum matching and a minimum vertex cover. Okay. And here's the tricky part. Okay. So what I'm gonna do is the following. I have this top vertices and bottom vertices, and y and z right here. Okay. Let's say my B, capital B is a minimum vertex cover, and it has one side. So this is R. So R is the subset of the vertex cover from the top set, V1. And T is the subset of the vertex cover from the bottom. Okay. Now, the way you pick your adjustment, epsilon, okay, is now you look at the edges. that are not covered by this minimum vertex cover B. Okay, you want to include one of these edges to your equality subgraph. Okay, let's say this is UV. U and V does not belong to the vertex cover. What does that mean? Well, capital B is a vertex cover for my equality subgraph, right? But both U and V are not present in the vertex cover. It means that the edge UV is not part of the equality subgraph. So UV is not part of the equality subgraph Y's. So I want to add one of these edges to my equality subgraph so that I can expand my equality subgraph, and later on I can create a perfect match. Okay, so to include it, so I take, let's say this is YU plus GV minus WUV, whose value is positive, just because this edge doesn't belong to the equality subgraph. Okay, and I take the minimum of those values. And the idea is that for each edge UV that doesn't belong to the equality subgraph, I want to reduce this value by epsilon. And because I took epsilon to be the minimum possible value, minimum value among them, one edge will have value 0 later on. And that edge will go inside the equality subgraph. Okay. And to do this, what we do is the following. Let me I mean, this thing might look artificial, but if you just look at it, this will get clear. So for the vertices inside T, you are adding epsilon. Okay, and for the vertices that are not part of R from V1, you are decreasing decrease the value by epsilon. Okay, let's look at this edge. The ZV will remain the same here. So ZV just becomes ZV. What about this edge? You have YU becomes YU minus epsilon. Okay, so for the edge that's outside the vertex cover, we have strictly less value by epsilon. So YU decreases, ZV stays the same. So YU plus ZV minus WV will decrease by epsilon. Okay. But for other edges, that's fine because so this is the only thing that you worry about. I guess you have other edges. Okay, for this one, also, okay, so for this edge, YU doesn't change and ZV doesn't change, so that's fine. Also, for this set, YT increases, but ZV increases, but YU decreases, so they stay the same. Okay, this is the way you expand the algorithm in the equality subgraph. So let's should I look at the example? Okay, so let's look at this example one more time. So here I have so this weights go to X right here, and 0 weights are assigned to the bottom vertices. Okay. Then if you assign each value compute yu plus zv minus wuv. Okay. If you look at their entries, you keep 0 edges, and this is your equality subgraph. Okay. Now I look at edges that are not covered by the vertex cover, which is R union T. And, you know, so the minimum, right, so the epsilon will be, so if you look at, I guess, this thing, that's not covered by R or T. So this edge it's not covered by the vertex cover. So epsilon will be 1 here. So you increase the value by 1 for the vertices that are part of vertex cover from Y. And for the vertices in X minus R, you decrease the value by 1. And so these values, 6, 7 goes to 5, 6. And 6, 8 go to 5, 7. And these values are increased by 1. And you get the next subgraph, the equality subgraph, and you compute the minimum vertex cover. And now, I guess you also have the epsilon is 1. So now you increase these values by 1, plus 1, plus 1, plus 1. And all the values from the top decrease by 1. So you get this assignment and this assignment. And that's it. You get a perfect match. Great. So you can prove that it will compute a maximum wave perfect matching in finite time. So observe that after each update, at least one edge enters the equality subgraph. Okay. So this is due to the way we design the algorithm. We take the minimum value epsilon, and we update the dual variable so that one edge will have value 0 for the gap. So this means that the number of iterations is order of V squared, because V squared is a total number of edges. Now, you gotta, the next thing you need to observe is that, let's say YV was your initial dual solution, and you get another feasible solution Y prime, let's see, Y prime G prime. And you just need to guarantee that this thing is feasible. And Y prime U plus G prime V minus WUV. You need to just analyze that, this value is always non-negative after the update. Okay. So Y prime U could decrease by epsilon or stays the same. and G prime V will stay the same or increase by epsilon. Okay, the one that increases doesn't matter because it will satisfy the inequalities. So we need to care about the edges UV where Y prime U decreases. So for U in V1 minus R and V is V2 minus T, we know that this thing is YU minus W. Okay, and Z prime V will be the same as the original value ZV minus WUV. And this thing has to be non-negative because, not W, sorry. Epsilon. Because epsilon was, if you go back to the algorithm, epsilon was chosen to be the minimum gap for vertices in V1 minus R and V2 minus T. So this value will be, because epsilon is the minimum value of IU minus YGV minus WV, it has to be non-negative. And the key point is that one edge will have value 0 after this update. And that will enter the subgraph. You also need to take care of, also argue that the edges that were already part of the correlated subgraph will remain the same. But that's leave it, that's left as an exercise. Okay, any question? Okay. Okay, I should have defined these notions beforehand. So, okay, let me just, that's a very good question. My apologies for confusing other people as well. So okay. I will just use the language of linear programming. Okay, so any X in RD is a solution. Okay, it doesn't matter whether whether this satisfies the constraint or not. It's a solution. A solution is called feasible if it satisfies the constraints. So a solution can be anything, but a feasible solution has to satisfy all the constraints. And like a solution feasible to the dual means that it's a feasible solution. Okay, that's, yeah, I should have defined this beforehand. So, in fact, I learned this algorithm last week. So even myself is not familiar with this algorithm, but I just learned it just to explain it to you today. What it means is that, I know how it works from the high level sense. I know that, this algorithm is out of the duality between the matching problem and this cover, the dual problem for the cover. I know how it works at the high level, but the details, I forgot about it for the last few years. But then I had to kind of, I just recovered my knowledge by reading the book. So my point is that I guess the algorithm is quite subtle, but when you write down maybe you're working on some combinatorial problem and you write your paper and you come up with your algorithm, I guess if you understand and digest like the basic flow of it, then you can sit down and work out with examples and deduce the correct algorithm. That's what you can do. Okay. So it's okay not to remember all this, the exact steps, but I want you to remember the basic idea. You have this primal problem, okay? And then you have this dual formulation. We know that they are, in the dual relationship. And one way to create an optimal solution is to find the solution that's feasible to the primal and feasible to the dual. And if they further satisfy this condition, which is the complementary slackness condition, then your solution will be optimal. Okay. And when you design an algorithm, you make it so that the complementary slackness is always satisfied. But now to create, now the question is how do you create a feasible solution? In our case, a matching is not feasible, but a perfect matching is feasible. So the question is how do you create a perfect matching out of this? And if you follow this outline, then my point is that this algorithm, even with setting this value epsilon, is kind of clear. Okay, if you just kind of look into the details, and the proof is also quite clear if you once you do this. Any questions? So this is Hungarian algorithm, and this is called primal dual method. And it's called primal dual method in the sense that our objective is to get an optimal solution for the primal. But to deduce the optimal solution for the primal, we also look at the dual. And we somehow use this relationship between the primal and dual. And I guess if you have learned convex optimization with constraints, you might have heard of this Lagrangian dual. And we talked about the primal dual algorithm, like primal dual gradient descent. And that's also has the similar idea. Like you look at the primal and the dual at the same time. Okay, just to illustrate, we are looking at minimizing convex function f of x subject to g of x at most 0. And we take the Lagrangian L x lambda, which is given by f of x plus lambda g of x. And the primal dual algorithm. So here, this is the dual variable. And this is the primal variable. And the primal dual algorithm does the following. So for xt plus 1 is given by xt minus gradient of some step size. You don't have to remember all these things, but I write down this to explain. And x L xt lambda t, and lambda t plus 1 is equal to lambda t plus eta t gradient with respect to lambda. So this is a primal dual algorithm in the sense that you are updating the primal variable and dual variable at the same time. Okay. Any question? Okay. Okay. For the next 15 minutes, I'm going to explain one application of bipartite matching. So we are pretty much the end of bipartite matching today, and I'll show you one example. Okay. I learned this topic when I was a PhD student, and this was a topic for MBA students. I guess MBA students were interested in kind of modeling their business problems using graph theory, and this is one typical example. Okay, so what is the problem? So we have a set of buyers and sellers in a marketplace. Okay, and so from now on, we're going to focus on the case of 3 buyers and 3 sellers, just to simplify our discussion. And so each seller has an item to offer, and buyers have valuations there that they have in their mind. Like there are 3 cars, maybe I rank the first one the most valuable, and the second as the second valuable, and the last something like this. So I have items U, V, W, and I have buyers X, Y, Z. And 30 is the valuation of X for item U. And 16 is the value of V to X. And 7 is the value of W to X. Okay. So in other words, let's say if the price of U is 25, then X will be willing to buy this item even if paying the price of 25, because still its valuation is 30, which is 5 larger than the price 25. But for buyer Y, its valuation is 23 for U. Thus the price is higher than its own valuation, so the Y doesn't have an incentive to buy item U. Something like this. So let me move on. So the sellers, or I'm a market designer. So I look at this kind of marketplace, and I have a right to set the prices of these items. Okay, and my goal is to match these items to buyers. Okay, like and so for each item, let's say item U, I'm gonna have set price PU, PV, and PW. And you cannot, make each buyer buy something. So you need to let them decide their own decisions. Okay, and each buyer is rational in the sense that they are behaving selfish fashion. They will choose an item that gives them the most profit. Okay, we cannot just kind of make the decisions for them. We need to induce their decisions. But as a mediator, what I can do is to set the prices of the items. So if the price is set too high, then maybe it will affect the decisions of the buyers. So that's how this market works. Great. So I'm gonna use Vij. So Vxu will be 30. So this denotes the Vxu. Vux, right? Vux. So it's the valuation of buyer X for this item U. For example, for VWZ will be 3. I'm going to use this notation for the valuation. Great. And the utility of buyer J, if it decides to buy item I, will be denoted as Uij. U stands for the utility. That is the profit, basically. So this is, if buyer J purchases item from seller I, then it will get this value of Vij, but it has to pay the price of the item, which is Pi. So this is the utility. So when each buyer looks at the list of items, it will choose the one that maximizes the utility. That's the rational behavior for the buyers. So this is rational behavior. Also, buyers will not get anything that gives negative utilities. You can just decide not to buy anything. That's more reasonable. So we want to basically find the assignments of between items and buyers that will be represented by bipartite matching. How the pricing mechanism are done is based on bipartite matching that I'm gonna explain now. So I want to find the matching and the social welfare. We need to look into the concept of social welfare. It's a summation of the profits of sellers and the profits of buyers. That is a social welfare. And as a mediator, as a market mediator, I want to induce that the social welfare is maximized. Can I do that? Okay. And I think that's the way Facebook used to do before. They want to make everyone happy. They are like advertisers and customers, and the Facebook wants to keep as many players as possible. So their objective was to increase the social welfare. Whereas Google's decision will be different. Google may want to just make sellers happy or buyers happy. They can have kind of different objectives. Because for social media platforms, I guess the number of users is the key objective. Whereas maybe like this searching platforms might have different business values. Anyways, so for today, we are interested in maximizing the social welfare. And it's given by this. So for all the assignments represented by Hij between buyer seller I and buyer J. This is Ij in M. I think the profit will be Pi because that's the price of the item. And the profit of buyer is Vij minus Pi. So the total social welfare is Ij in M, Vij. Okay, so let's look at this thing. Social welfare equals the summation of the valuations over the assignments. And if you remember that M is a matching, bipartite matching. So maximizing the social welfare is equivalent to maximizing the finding a maximum weight matching, where each weight is given by this valuation, Vij. Okay. Is there any question? But the difficulty behind this is that it's not like we compute the bipartite matching, a maximum weight matching, and just give them to these players. It's that we set the prices so that everyone behaves in a selfish fashion, and we want to induce that all people are happy, and in the sense that they choose their selfish decisions. But if you want to induce that the final outcome is a maximum weight match. That's what we want to do. Okay. So now I'll explain like how to do this. So let me Move on. So individual buyers have, but it could be that there are some conflicts between buyers. Maybe two buyers have the same like the same item the most. In that case, we cannot assign this single item to two people. So we need to. This is a competition situation. In that case, maybe this item is too popular. Then to avoid this conflict, as a mediator, I can increase the price of it. Okay, it's like an auction. So two customers participate in an auction, and they still like this item, and they compete. And so what the auction market does is increase this price by some amount in every iteration until one person gets out, and okay, that is the deal. So we're gonna set a high price. So and later, the final set of prices is called market clearing if there's no conflict and we can induce a perfect assignment. That is, I'm going to quickly explain how it works. And the pricing mechanism is due to these three people, and they got the Nobel Prize in economics for this, I think in the 1960s or something. Even this concept is pretty old one, but it's interesting. So this is called the VCG mechanism, which stand for the three inventors of this. So the basic idea is the following. So whenever there's a conflict, like two people like a single item, or three people like two items only, in that case, we increase the prices of those items in the conflict. That is the idea. To capture this thing, we use this notion of preferred seller graph. That is the following. So for each buyer, they indicate the item that they most like. Okay? They choose a single item or a few items that are most preferred by that buyer. So for buyer X, it likes you, okay, and it likes you more than the other items, and also Y likes you more than the other items. The same holds for the last buyer. Okay? And we get a conflict, right? So what I do is I increase the price of this item, which is in the conflict, until I get a different preferred seller graph. So what I do is, so I have this thing. What I do is I'm gonna increase the price of U by 6. Okay. Then the valuation will be, this thing will be 24. This will be 7. And this will be 17. Right? Still, for buyers X and Y, U is the most preferred item. But if you look at buyer Z, Z now becomes neutral between U and V. You can add on it like this. You get a different graph, which is this. Okay. Still, we have a conflict, right? There's no perfect matching by the Hall's marriage theorem. We have the neighbor of U, Y, Z, X, Y, Z will be U, V. So there's no perfect matching. So in that case, maybe U and V are too popular. So what I'm going to do is I'm going to increase the price of U and V by 4. Okay, then now it becomes 10. Now the price of V is 4. Let's compute the value, the utility. Now this becomes 20, 13, 3. the valuation for 16 is 12, 10, and 3. Okay. For X and Y, still the item U is the most preferred item. But for Z, Z is neutral with all these 3 different items. So if you draw the preferred seller graph, you get this graph, this one. You still have a conflict. So I think, all right. So for X and Y, you have X, Y likes U most. So what I do is, okay, I increase the price by 3. And now the price becomes 13. Then if you compute the valuation, it's 17 and 10, 10, 3, 3. This is, I think, 12. Now, Y becomes neutral with items U and V. So now the final graph will be this. And there's a perfect assignment, which is this and this. I explained this mechanism in pictures, but you can prove that the mechanism always finds a market clearing price that always gives you maximum social welfare in finite time. I'm gonna start the next lecture with proving this. So let me stop here and I'll continue in 15 minutes.